wrap up, I want to stress that this is really just a first step, but a major step towards overcoming the water surface boundary, which has remained until now an obstacle for communication. The new aspect of this technology is that we are transforming this water surface from an obstacle itself into communication medium. And as the research evolves, we hope that it will pave the way to many other applications, from submarine to airplane communication and ocean exploration. With this, I would like to wrap up my talk, and I'm happy to take any questions. Thank you.
Hello. Yeah. Hi. I'm Suraj Jog and I'm from UIUC. Firstly, very interesting talk. I had one question. What if you had interference in the form of, say, rain? So that might add interference along the same frequency spectrum at, say, 100 hertz to 200 hertz. So how would you filter that out?
So first of all, that is a very good research question, and one of the directions that, or one of the questions that needs to be answered in bringing this system into more practical scenarios. And in handling the interferences, we will have to develop a way for us to detect what frequencies will be will be attenuated significantly by the conditions like the rains, so that we can use other bandwidth or the carrier frequencies.
Thank you.
Hello, Luis Pedrosa, EPFL. Wonderful talk and a wonderful idea. Thank you very much for bringing it up here.
Could you
speak to the microphone?
I'm 6'4". It's not going to be easy.
Okay.
So this has been a challenge for many years now. I played around in the acoustic modems underwater in a previous life. I'm kind of curious how you would adapt this to work in more real-world scenarios. In particular, the way you described it, it seems to suggest that the underwater signal has to be directed directly up, so that the pressure wave is moving water in the perpendicular to the surface of the water. Do you have any idea how this would work if it wasn't pointing up, but sort of sideways, and up to what distance it would work? And then also on the top side, up to what distance can the radar be from the surface of the water itself, which would be indicative of if this would be feasible with, say, a satellite, for example?
So I guess the first question has to do with the angle of incidence of the acoustic signal on the surface. And in that regard, unfortunately, we have not performed an evaluation on that scenario itself. But it is correct that this system will perform optimally when the speaker is transmitting directly in the water column itself. And one impact that I can see is the degradation of the SNR when it is slanted to the other surface, towards the surface. But I feel like this will be something that we will have to delve deeper into answering the question. And the second question was, can we bring this up to a point where we can transmit from a satellite? Or until what distance can we transmit a signal to get enough SNR for valid communication in the air? And in our scenarios, we used, the radar was atop the surface from 20 centimeter to 40 centimeter. But we expect this to scale because RF is the best method for it. RF communicates and travels well in the air with less attenuation. And given the distance of the aircraft example that we were going for, we feel that it's going to be affected by, the attenuation is mostly affected by the spherical expansion of the distance itself, and that we will be able to scale to those distances. But as for the satellites, I am not entirely sure, and I do not want to make an incorrect answer, so take off that.
Let me try to get maybe one or two more questions. Brief.
Thank you.
Both questions and answers. Yeah.
Okay. Shuman Banerjee from University of Wisconsin on this side. Hi. So great idea. I love the presentation. But I had a question about the applications you started out with. So you talked about submarines and scientific exploration and finding missing planes. But the way you described your experiments, I'm wondering, the depth is significantly larger. Do you anticipate those applications will benefit by a solution like this, or the power required for a speaker would actually be able to ever overcome this issue at all?
So I think the question is, how deep can this work? And to answer this question, yes, we have done experiments up till only 3.6 meters, but our theoretical calculations and simulations show that it will be able to scale much better by increasing the power that we're transmitting at. And in fact, in the lower frequencies in the underwater communication, we can communicate as far as several kilometers. And that is because we're able to propagate, the acoustic signal can propagate really well in the water compared to what RF can. And so we believe that it will be able to scale to a depth that is required for the application.
But isn't it true at the lower frequencies you'll have issues with confusion with the water zone oscillation frequency? Because right now you're at a different frequency, so or is that not a problem?
So we were transmitting at the center frequency of 150 hertz with a bandwidth of 100 hertz. And depending on the scenarios and the environments that we use, we can also always switch to a different frequencies, knowing what the situation is going to be. But the reason that we choose to use lower frequencies is because it propagates well and it allows us to have much higher SNRs on the surface itself.
One more question.
Okay, hi, I'm Jae-Hong Lee from Seoul National University. Okay, you said that you can use rate adaptation algorithm, but how can it be done without any acknowledgement frame?
So the question is, how can we adapt to the channels not getting any feedback from the receiver? And in the paper, we detail that this SNR can be estimated because the factor that contributes the most is actually the depth itself. And today we can use a highly sensitive pressure meter to estimate the depth. And by knowing that, we're able to estimate what the SNR is going to be so we can allocate different powers at different frequencies.
Okay. So since there were a lot of questions on oscillations, I just had a quick comment that maybe, even if you use a depth camera to just estimate the noise distribution, you might be able to do a better job of filtering out the noise. So if you just use depth and use it in a synthetic aperture-like manner, just to estimate what the distribution of noise might be, you might be able to subtract that out better from the signal. But
Okay.
that was just a comment.
Thank you for the idea.
Okay. All right. So let me introduce the next speaker. Our next speaker is Deepak Vashisht, also from MIT.
Talk about how we can communicate with and localize devices inside our bodies. This is joint work that was done as a collaboration between our group at MIT and two doctors, Dr. Xiaoming Liu and Dr. Jay Flans. So let's go, Omi, Dina, and two doctors. Every year at Sigcomm, we like to talk about different kinds of networks. We talk about wired networks like the internet, data centers. We talk about wireless networks like Wi-Fi, LTE, so on and so forth. Today, I'm going to talk about something different. I'm going to talk about in-body networks. In-body networks are just networks for devices that can be implanted inside our bodies and that need to communicate data outside. Why do I care about such networks? I care because the field of medicine around us is changing. It's going through a sea change, and a lot of that change is happening because of devices that can be implanted inside our bodies. Let me give you two examples. I'm sure some of you have seen these smart capsules that have tiny cameras on them. You can swallow these capsules, they can go through your body and take pictures of your GI tract. A doctor can look at those pictures and see if you have any abnormality, if you have a disease or a tumor or an ulcer. So clearly, we want to be able to communicate with these capsules. We want to access their data. We want to see what they're seeing. And at the same time, ideally, we would also want to locate them. We want to find out exactly where a capsule is when it's taking a picture. And then you can program the capsule to do interesting stuff, like, say, take more pictures in the small intestine or deposit a medicine in the stomach. Another application that I deeply care about is cancer radiation therapy. So in cancer radiation therapy, you deliver a high dose of radiation to tumor cells so that they die. But think about breast tumors or lung tumors. Those tumors move as you're breathing. And as a result, the beam is going to miss the tumors and hit healthy tissues around it. It can be very dangerous if the tumor is close to your heart or your lungs, which are very sensitive tissues. So what doctors want to do today is to inject small markers inside these tumors so that they can track the tumor by tracking those markers. And then they can steer the beam along with the tumor so that they hit the tumor and don't hit healthy tissues around it. And these are just two examples. There are a lot of other applications of in-body devices. For example, microrobots that can travel through your body and do targeted drug delivery or do in-body biopsies. And for all of these applications, we want to be able to communicate with these devices. We want to get access to the data that they're sensing. And we want to be able to locate these devices. We want to track them as they're moving through our bodies. So hopefully, now we all agree that we want to do in-body communication and localization. How can we do that? So of course, we're going to use wireless signals for that, because as we all know, wireless signals can be used to communicate, and of late, we've seen that they can also be used to locate devices. But what kind of wireless technology do we want to use? Can we just take existing technologies like Wi-Fi and LTE and put them on devices inside our bodies? Unfortunately not, right? Because these technologies have high power demands. What we really want is something that's really power efficient, ideally something that requires zero transmission power. And as some of you might know, backscatter networks do exactly that. So backscatter networks rely on reflections and do not generate any transmission power of their own. We've talked about backscatter in the last few Sigcomms. I'm going to give you a very high-level overview. So let's say there's this access point on the top that wants to talk to this device, backscatter device on the bottom. So what it's going to do is going to just send a signal, let's say a simple sine wave, and this device is just going to reflect that signal back. And by modulating that reflection, by turning it on or off, it can communicate bits of information. So if it wants to say bit 1, then it's going to reflect the signal back. If it wants to say bit 0, it's going to not reflect the signal back. It's as simple as that. So backscatter networks are great. They're very power efficient. We want to apply them inside our bodies. Can I take this system, put this exactly as is inside my body, and will it work? As it turns out, the answer to that question is no. And that's going to be the focus of my talk. I'm going to talk about how wireless signals behave completely differently inside human bodies as opposed to air, and how that leads to challenges for both communication and localization. And then I'm going to present to you a system called Remix, which can solve those challenges and deliver an in-body backscatter communication and localization system. Let's start by talking about communication. So this time, again, we have an access point that wants to talk to this capsule, which is placed inside the human body. And we're going to do backscatter, so this access point transmits a signal. But most of the signal is just going to be reflected off the skin, and only a tiny portion is going to go inside. And even this tiny portion that goes inside is going to attenuate further. It's going to attenuate exponentially inside the human body. And this is how wireless signals are completely different inside human body as opposed to outside. In air, when we talk about attenuation, it's polynomial. We talk about d square or d cubed depending on the distance. But this is exponential. And then the signal has to go back through the human body and get back to the access point. By the time it actually reaches the access point, it's very tiny. It's 100 million to 1 billion times smaller than the reflection from the skin. It's as if you're in a room where someone is shouting and you want to listen to a soft whisper. You cannot do that, nor can this device. And that's the exact problem we want to solve. We want to separate these tiny target reflections from the huge skin reflections. So in this graph, actually, I'm not even drawing the target reflection to scale because otherwise you won't see it. So how can we do that? We want to take these target reflections and extract them out. Do we have ideas? Let's try this. Let's throw more power at the problem. We're going to transmit more power from the access point. What's going to happen? Well, both skin and target are going to reflect more, and the ratio does not change, so it does not help me at all. Okay, here's another idea. Let's try to just transmit more power from the target by putting an amplifier inside our bodies. So first of all, if you are going to do that, you're going to need a huge amplifier because the ratio is so large. And then amplifiers are active devices. They need batteries to operate. So if you're going to need huge power inside our bodies, why don't we just use Wi-Fi or LTE anyway? So what we really need is a simple passive solution to this problem. We want to be able to extract these tiny reflections out, but we want to do that in a simple and passive way. Our solution is to use a Schottky diode. So if you don't know what a Schottky diode is, don't worry, I'm going to tell you now. It's a really simple and small device. It's smaller than a millimeter. You can buy it off the shelf. It's completely passive, requires no power at all. And the most interesting property that we're going to leverage is that it has nonlinear behavior. So ideally, most wireless circuits are designed to have linear behavior. But this diode is nonlinear, it's non-ideal. And I'm going to tell you what this nonlinearity means for us and how we're going to use it. So let's see how I can use this diode. So I can take this diode, put this inside this capsule here. And this time, instead of transmitting one sine wave, I'm going to transmit two sine waves. One at frequency f1 and another at frequency f2. Let's see what happens. So like before, the skin is going to reflect a large part of those signals. So there's going to be reflection at f1 and reflection at f2. But this diode is going to do something different. Because it's nonlinear, it's going to mix those frequencies together and create new frequencies. So it's going to create reflections at f1 plus f2, 2f1, 2f2, 2f1 plus f2. And that's because of its nonlinear behavior. So this diode is like a DJ that can remix these signals together and create new frequencies. And then I can look at these signals in the frequency domain. I'll have huge signals from the skin reflections, but they are at original frequencies f1 and f2. And I'll have tiny reflections from the target, but they are at different frequencies. And they can just apply a frequency domain filter to get access to the target reflections and remove the skin reflections altogether. So what I've done, we've used a Schottky diode, which is a passive device, to shift signals away from each other in the frequency domain. This leads to a very simple circuit design for us. We have a diode that's directly connected to an antenna, and you can turn reflections on and off to communicate bits of data. So one of the interesting pieces of this design is that you can create large frequency shifts because you have the choice of choosing f1 and f2. You can choose them and create whatever shifts you want. So I've told you how Remix can enable communication from inside the body by filtering out skin reflections. Let's talk about localization. So as I said before, we want to be able to track these devices as they're moving inside our bodies. How can we do that? Well, before I tell you how we do that, let's take a step back and try and understand how localization in air works today. So let's say there's this capsule that I want to localize, its location is XY. What I'm going to do today is take an access point, measure the angle from that access point, draw a straight line, and get one equation. And then I can do it from another vantage point, intersect those two straight lines, and get the location of the device. This is a simple principle called trilateration. So what changes inside the body? And to tell you that, let me bring your attention to this picture. I'm sure you've seen this in high school physics. When you try to look at objects inside water, they appear to be at a different location than they're actually at. And that's because of a simple principle called refraction. So when light, which is an electromagnetic wave, travels from one medium to the another, it bends at the interface. And similar to that, radio waves are also electromagnetic waves, so they're also going to bend at the interface between air and human body, and they're going to experience bending. And this is actually a simplistic picture of the human body. Like, human body is not monolithic. You can zoom into just one portion here, and you're going to see multiple different kinds of tissues. You're going to see skin, fat, muscle, colon. And there's going to be bending at each of these interfaces. There's bending at air, skin, fat, muscle, colon. So what this means is that if you rely on existing models that model propagation as straight lines, you're going to get a wrong estimate of the location. So anything that's in your colon might appear to be in a stomach or appear to be in your liver. It just does not work. So you cannot rely on existing models that model signal propagation along straight lines. You have to do something different. Our solution is to use localization model with splines. So instead of modeling signals with straight lines, you model them with splines. And in our case, splines are just a set of line segments. So we get one line segment for each tissue type, one for skin, one for fat, one for muscle, one for colon. But wait, there's a problem. Human body is too complex. There's so many tissue types. You don't know how many layers of tissues that the signal is going to go through, exactly what those tissues are, and you don't even know what's the thickness of those tissues. And then my body is different from your body. So your body might have more muscle or more fat than my body. And I cannot really have access to that information beforehand. I cannot really cut you open, look at your tissue layers, and put them in my algorithm, right? So I want to model this complexity of the human body, but at the same time, I want to design an algorithm that does not have access to this information beforehand. To do that, we have two observations that help us. First of all, we observed that in terms of electromagnetic properties, all human body tissues can be divided into two main categories. There's a class of tissues which is similar to oil. For example, fat, colon, breasts, bone marrow, bone cortical, all those tissues have electromagnetic properties that are similar to oil. And there's another class of tissues like muscle, skin, cornea, blood, all of which have electromagnetic properties that are similar to water. So what I can do is that instead of modeling multiple different kinds of tissues, I can just model two kinds of tissues, water-based tissues and oil-based tissues. So that simplifies the problem a little bit, but there are other problems because you don't still know what's the order of those tissues and how many tissue types there are. To solve that, we have the second insight. So here's a lemma that I'm stating informally here and that we prove in the paper. What it states is that the phase of the wireless signal does not depend on the order of the tissues. And as you might know, wireless localization depends on wireless phase. And what this lemma says is that the phase is independent of the order of the tissues. And let me tell you what this means. What this means is that let's have